Descriptive mineralogy. Welcome to the physical properties of minerals. So this section, it is a part 2. Actually in the part 2 I have covered like form, color, the other things. So here in this part 2 I'll be covering the physical properties of minerals, and the detailed topics to be covered are streak, luster, fracture, magnetic properties, electric properties, fusibility and specific gravity. So coming to streak. So streak, what is a streak? Streak of a mineral is exactly the color of the fine powder of a mineral, and it differs from one mineral to another mineral. So with metallic ore minerals, generally streak plays a very dominant and significant role. For example, if you take pyrites, pyrite is Fes2 and galena is lead sulfide PbS. So this pyrite, it exhibits its a brassy yellow color, and galena, it's a gray color, but both exhibits a black streak. So that means even though pyrite is yellow and galena is gray in color, but they both exhibit a black streak. It's a striking feature. So how do you measure the streak? It can be measured with a streak plate, which is a piece of porcelain unglazed thing, and which is used to create streaks by scratching or rubbing a mineral across it. So the hardness of the streak plate is 6.5. So coming to the lustre. So what is a lustre? Lustre is nothing but the nature and quantity of the light which is reflected on a mineral surface is known as a lustre. There are different degrees of lustre. That means basing on the amount of the shyness. So these lustres are divided into different degrees. So number 1, splendid. Number 2, shiny. Number 3, glistening. And number 4, glimmering. And 5, dull. So here what is splendid? Splendid means suppose a mineral surface is so brilliant and it's similar, it reflects the objects similar like a mirror. So here the objects are very bright, and so that the mineral surface is so brilliant. So this type of a luster is known as a splendid. And coming to shining. So what shining means? It's less bright surface with slight reflections of objects. And what you can see in the glistening is, it's still less brilliant than shine. And glimmering means it is still less bright than the glistening. And dull means when there is no luster at all on the surface of a mineral, then it is known as a dull. Then what are the types of the lusters? So number 1, you can see the metallic luster. So what is the metallic luster? The ordinary luster of all the metals is the metallic luster. So the excellent examples we can say gold, iron pyrite, galena. So all these, they exhibit, any metal will exhibit a metallic luster. Suppose if it is submetallic, means when this type of luster, when the luster of the metals is not that much displayed. So when poorly displayed, this type of the luster is known as a submetallic luster. An excellent example is chromite and cuprite. So these are the minerals which exhibit the submetallic luster. And coming to the vitreous. So what is a vitreous? Most of the minerals exhibit this type of luster. So that is the luster of a broken glass. So when less developed, it is termed as a subvitreous, and when it is not developed at all, then it is also called as a dull type of luster. So these are well displayed, especially among all the silicates and also carbonates, sulfates, halides and other non-metallic minerals. And quartz shows the vitreous luster. Most of the silicate minerals also shows this vitreous luster. And pyroxenes and amphiboles, they show subvitreous or dull type of luster. The another type of luster is resinous luster. This is the luster of a resin, and you can see the examples like opal, amber, sphalerite. Sphalerite is a zinc ore. So most of the questions can be asked like this, like chromite exhibits which type of luster? So it shows metallic, it's a submetallic luster, and cuprite also, it shows submetallic luster. And suppose if you take opal or sphalerite, what is the luster of the sphalerite? It is similar to, that means the luster of a resin. So that's why it shows resinous luster. Then another type of luster is known as a pearly luster. So what is this pearly luster? The luster of a pearl, and it is shown by the surfaces which are very parallel, to which the mineral surface can be again drawn into thin plates. Suppose if you take talc, hydrous magnesium silicate, and then brucite and selenite, it's a variety of gypsum. So all these minerals, they exhibit pearly luster. And another is silky luster, the luster of the silk. So this is peculiar to minerals which possesses especially fibrous structure. Suppose if we take asbestos or gypsum, so these varieties exhibit silky luster. Suppose if we take the fibrous variety of gypsum, it is known as a satin spore, and this exhibits a silky luster. And similarly, fibrous varieties of asbestos are called as amianthus. Amianthus is a variety of asbestos. This also shows silky luster. So questions like suppose which variety of what is the luster of asbestos? So luster of the asbestos is silky. Similarly, the luster of gypsum or satin spore is silky. So like this, the questions will come. Then coming to the fracture. So what is a fracture? The type of the fracture seen on the mineral's fractured or chipped surfaces. Various terms are there to describe fracture. So here, number one, you can see that there are a number of types of fractures are there. Number one, conchoidal. So what is conchoidal means? When the mineral breaks with a curved surface or convex fracture. So the excellent example you can see quartz. Quartz shows excellent conchoidal fracture, and similarly flint. So it is also a variety of silica, and then obsidian. So all these minerals, they show conchoidal fracture. Then what is even? Even means when the fracture surface is very flat, then it exhibits even fracture. So excellent example, chert. And then uneven. So what is uneven? The fracture surface is rough due to some elevations and jagged depressions like that. So here most of the minerals, they have uneven fracture. And hackly. So what is a hackly means? Here the surface is embedded with elevations, but it will have sharp and very finely cut and jagged elevations. Suppose if we take cast iron, it exhibits hackly fracture. And another type of fracture is earthy. So this is dull fracture. When the fracture is very dull, it is known as a dull fracture surface, that is earthy. Excellent example, chalk and mirchasam. Then coming to the magnetic properties. So what are the magnetic property? Means a mineral possesses a magnetic property when it attracts towards a magnet. Some of the minerals, suppose if you take in the natural state, they are capable of attracting the pieces of iron, just like a magnet. So such minerals are called as a natural magnets. So we can see the example like a lodestone. It's a variety of magnetite. So magnetite is Fe3O4. So here, depending upon the magnetic property, minerals are again classified into three types like ferromagnetic, paramagnetic and diamagnetic. So what is a ferromagnetic? Some of the minerals, suppose if you take in their natural state itself, they are very attracted or strongly attracted by a Bohr magnet. And these minerals are said to be ferromagnetic, and this property, whatever the property of strongly attracting a magnet, is known as a ferromagnetism. And examples are magnetite and pyrrhotite. These are the examples for ferromagnetic minerals. Then what is paramagnetic? Paramagnetic means these are not that much strongly, but these are attracted slightly by a magnet. Such minerals which show this paramagnetic are known as a paramagnetic property. So this property is known as a paramagnetism. And all minerals, the minerals whatever it may be, which they contain iron, are said to be paramagnetic. And some of the minerals like beryl, so it's a cyclosilicate, tourmaline, and then spinel, monazite, etc. So these minerals which do not contain iron, even though they do not contain iron, they are also paramagnetic. So coming to the another magnetic property, that is diamagnetic. Some of the minerals which are repelled slightly by a magnet, that means they are not attracted, they are repelled. So such minerals are known as a diamagnetic, and this property is known as a diamagnetism. If you take quartz, calcite, feldspar, topaz, corundum, and corundum is aluminum oxide, cassiterite, it's a zinc ore, blend, it's a zinc ore, and then blend, zircon, wulfenite, etc. All these minerals, they exhibit diamagnetic property. Then coming to the electricity property or electricity, the minerals maybe develop, some minerals, they exhibit electricity either by due to rubbing action, that is known as a friction, or by heat, in the, whatever it may be. So in such case, they are said to be pyroelectric. Excellent example, tourmaline. So there are type basing on the electricity, the minerals are divided again good conductors and bad conductors. Conductors means they conduct electricity. Suppose native metals, graphite, sulfides, except blend, so they are very good conductors. And bad conductors like the blend, that is known as a sphalerite, that is a zinc ore, and then quartz, calcite, barytes, fluorspar, that is calcium fluoride. All these minerals are said to be bad conductors. So minerals showing the electrical properties are not that many, but these are not very useful in the identification of minerals, but there are types of electrical properties. Number 1, frictional electricity. Number 2, pyroelectricity. Number 3, piezoelectricity. So what is frictional electricity? So some minerals, suppose if you take diamond, it may become electrified when they are when it is rubbed with a piece of cloth or with a piece of fur. Then these minerals, they become electric. They possess the electric property. So they attract bits of the paper. This property is known as a frictional electricity. And what is pyroelectricity? The simultaneous development of both positive and negative charges of electricity on different parts of the same mineral crystal by bringing some changes in the temperature. These are known as a pyroelectricity. Some of the crystals which do not possess the center of symmetry show this property. That means the crystals which do not possess the center of symmetry, they exhibit the electrical property, especially pyroelectric property. Only non-conductors show this type of property, and this was first observed in the mineral tourmaline. So this serves as an excellent example. Pyroelectric mineral is the tourmaline. And coming to the piezoelectricity. So in some minerals, the electricity can be developed by means of by applying certain type of pressure. So this type of electrification is known as piezoelectricity. And here also the crystals which do not possess center of symmetry, they show this type of piezoelectric property. If you take all the minerals, of all the minerals, quartz is the most important piezoelectric metal, and it is because of this property, quartz is used in electronics industry. So coming to fusibility. So what is this fusibility? So fusibility is nothing but it's a character of a mineral which depends upon the heat. The relative fusibility of certain minerals is a useful character or significant character which will be helpful for identification of the mineral, and this can be determined by a blowpipe. And here a scale of 6 minerals are there, of which the temperature of fusion, it was supposed to increase step by step, and this was suggested by von Kobel. And in this von Kobel's fusibility scale, the minerals are stibnite, natrolite, almandine garnet, actinolite, plagioclase, and olivine. So these minerals are there from top to bottom. So here if you see the von Kobel's scale of melting point, suppose if you take the stibnite, it has the approximate melting point 525 degrees centigrade, and if you take natrolite, it has 965 degrees centigrade, and almandine garnet 1050 degrees centigrade, and actinolite 1200 degrees centigrade, and plagioclase 1300 degrees centigrade, and olivine it has 1400 degrees centigrade. Coming to specific gravity. So the specific gravity of a body is the ratio of the weight of the body to that and equal volume of the water. So here the weight of the water, it varies with the temperature, and this has to be considered in the exact works. And the specific gravity of minerals, it depends upon the atomic weight of the constituent minerals and the way how the atoms are packed in the crystal lattice. And suppose if we take the non-metallic minerals like silicates, sulfates, carbonates, halides, nitrates, etc., they have specific gravities varying from 2.5 to 3.5. And suppose if we take the metallic minerals like sulfides, oxides, and other native elements, they have specific gravity varying from 5 to 8. Then what are the methods for determining the specific gravity? Suppose if we take the fragments of a solid mineral about the size of a walnut, very small size, that it's about the walnut. If you would like to measure the specific gravity of these fragments of a solid mineral about the size of a walnut, the chemical balance is used. And suppose if you would like to measure the specific gravity of large specimens, Walker's Steelyard balance is used. And for very small specimens, we will be using the Jolly's spring balance. And what is a pekinometer or a specific gravity bottle? So this is usable for friable minerals or liquids and heavy liquids. So these are used for the separation of mineral mixtures into the pure components according to their specific gravity. So heavy minerals can be identified by the specific gravity of these can be identified with the help of heavy liquids. So these are the references. Thank you.